Welcome to Energy Twin Interactive. The first step in creating a model is assigning the point. Then select base period, aggregation, and aggregation period. When choosing the base period, the whole year is the best option. Now let's start with the monthly aggregation period. After setting all these parameters, you will see your data. The chart on the right shows the relation between outside temperature and the amount of energy per month. Each point represents 1 month and the line shows the model. Here, you can see the comparison between measurement and the model. The middle table contains all the data that are shown in the chart. We can select any data point and see it in the context of the graph. You can choose a model in the top left table. Here, you can find the statistical properties of the currently identified model. The green color indicates that the metrics fulfill the M&V guidelines. Now, let's focus on the model itself. We will start with the manual setup. Upon clicking on the manual setup, you can see all the supported model types. 2-parameter model, 3-parameter heating model, 3-parameter cooling model, and so on. Pick any you want and immediately see the imminent change. The results are somewhat strange, and the reason is the fact that we haven't correctly set the heating change point. When looking at the data, we would expect the heating change point to be somewhere around here. So let's change the value to 16 degrees Celsius in the manual setup settings. As we can see, the new model fits much better. Suppose you don't want to tune your models manually. In that case, you can also try auto change point setup, which evaluates all the variants of the change point and chooses the optimal one. Our initial estimate of 16 degrees Celsius wasn't so far-fetched, since in this case, the optimal heating change point is 14.4 degrees Celsius. Moreover, you can avoid this manual process by selecting one or both models and using the complete auto setup option. As a result, a pop-up window will appear with all the possible model combinations and their performance. The optimal model is selected based on these results, and you can see the full overview in the table. There are 2 categories of supported model types: change point models and degree days models. Let's choose the heating degree days model next. Now, the x-axis corresponds to the outside temperature, but in the unit of degree days per selected period, in this particular case, a month. Before we move on, let's switch back to 3-parameter heating change point model and try different aggregation periods, for example, a weekly one. With the weekly aggregation period, we can see that in the statistical properties table, the model is still good, so let's look at daily data. The problem with daily data is that there could be a completely different regime during the working days and the weekend. From the visualization chart, we can see that this also applies to our example. There is a significant drop in energy consumption during the weekend, so we need to add a setback, which can be done by choosing daily with the weekend setback aggregation period. Now, there are suddenly 2 models instead of 1. There is a separate model for the weekend and for workdays. Each model can be tuned manually. Pick a model type, try adjusting the change point, or use the auto change point setup option. We will use the complete auto setup option on both models. From the results, we can see that the best model for the weekend is the 3-parameter heating one, and for workdays it is the 4-parameter model. As you can see, we didn't fulfill the measurement and verification criteria for the weekend model, which doesn't mean you shouldn't use the model, but keep in mind that there are some uncertainties during the weekends due to the lack of data. On the other hand, the model is good during the workdays and the combined one is acceptable. When you confirm optimal models for each subset of data, you can investigate them individually or investigate both using the combined model. Now, let's save the model and you will find it in the Administration tab. Let me show you how to work with outliers in this example. Outliers significantly affect the model. Based on the data visualization, we can immediately see suspicious data points, our outliers. Current statistical properties make this model unacceptable, so what can we do? Let's sort the data points by measured value, which allows us to find the outliers quickly. Select the outliers and exclude them using the Exclude Selected option, after which the outliers will turn red. After tuning the model again, we can see some improvement in the model shape and statistical properties. By adjusting the settings, you can either observe data with outliers or hide them. If you change your mind, you can either include outliers of your choice again, or reset all excluded points by clicking on Reset Excluded option. Once you have a saved model, you can see the prediction compared to the measurement and work with the model further. Let's have a look, starting with the base period same as used for the model identification. In the top chart, there is the cumulative difference. You can see a 0 cumulative difference as expected, since the span is the whole year. The measurement and prediction are depicted in the middle chart and temperature in the bottom graph. In order to investigate measurement versus prediction chart in detail, you can hide the weather and cumulative charts. Let's have a look at a different evaluation period, the year 2020. We used the year 2019 for model identification and now expect similar behavior. The year 2020 was highly unusual due to COVID-19 pandemic. With the first wave in spring, a lot of restrictions and lockdowns were introduced, resulting in significant savings in energy consumption, precisely 22%. This trend can also be observed in cumulative difference that goes down. That is all from Energy Twin Interactive. Stay tuned for more.